Hello, my name is Maxim Skripnichenko. I'm PhD student from Moscow Institute of Electronic Technology. Today I will tell you about a method for developing algorithms for calibrating an ADC. The main objectives of this work are describing the method of development and verification of ADC algorithms in the early design stages, creating an ADC model composed of a capacitor array model, a comparator mismatch model, a comparator noise model, analyzing the effect of capacitor mismatch on the key characteristics of the ADC, signal-to-noise ratio and spurious free dynamic range, and developing and verifying a digital algorithm that reduces the effect of capacitor mismatch. Here are the topics that will be covered during the presentation. The graph on the left shows the various ADC architectures and their applications. As you can see, users face a trade-off between ADC speed and resolution. At the same time, users want to have ADCs that are both fast and high resolution, while consuming less power and have a number of other characteristics. And there are some restrictions. For example, input offset of differential pairs, or the capacitor mismatch during fabrication, which don't allow to obtain the required characteristics. Overcoming of these limitations require the development and improvement of the algorithms using in the ADC, which entails an increase in simulation time spent on debugging and verification algorithms. This leads developers to look for new ways to accelerate modeling at the early phase of design. Next, we will consider the main options for representing the analog part of the ADC, which can be used to develop and debug the digital part. Full schematics gives the most accurate results and allows you to take into account all effects, but it takes a lot of time to simulate. In addition, block parameterization is severely limited. Using ideal elements in schematic or Verilog A reduces simulation time, but makes it impossible to use Monte Carlo or noise simulation. In addition, the options for parameterization are also limited. Using real number modeling allows to have only a digital simulator, but likewise leaves no ways for Monte Carlo or noise simulation. In addition to speed, there is another disadvantage. There is a need to use RTL written in Verilog, System Verilog, or VHDL. With this approach, it is necessary to develop implementation of algorithm before it's verified, and only then evaluate its effectiveness. If the algorithm fails, a lot of time will be wasted. What the reason for the long calculations of ADC switching? Let's take a look at the picture which shows a graph of capacitor charging. At the initial moment T0, the voltage on the capacitor is equal to 0, and after several time intervals, it is charged to the maximum voltage. Circuit simulators like HSpice will calculate voltage at each time point from 0t to 6t, while in the early stages of ADC design, such accuracy isn't required, and only 0t and 5t moments are interesting. Hence, it follows that for the initial stages of ADC design, a model that doesn't take into account transient and calculates the state of the system only at the initial and final points of transit is needed. The following slides will be devoted to the development of such a model. Let's take a look at the block diagram of the ADC. The picture shows capacitor array and sample hold unit at the part of the digital to analog converter, comparator, and digital core. The digital part of the successive approximation register implement the binary search algorithm. So let's take a closer look at analog components. There are several options for the capacitor array architecture. The most commonly used are three of them. First, the simple binary array, where each capacitor is twice the next. One sampling key, K0, is required, but for a large number of bits, this array cannot be physically implemented. The next one is C2C array, where each capacitor is in a separate section with its own K0 key, and all bit capacitors are equal. The disadvantage is that with the large number of keys K0, different voltage values can be sampled in different sections because of jitter on the keys, which limits the maximum signal-to-noise ratio and the number of effective bits. And the last one is split array, which is a kind of compromise between the binary array and the C2C array. On the one hand, it doesn't require many switches, which reduces the SNR limitation. And on the other hand, there is no need for large capacitors. In this case, it is necessary to calculate the value of the dividing capacitor to preserve the binary inter-bit ratio. The basis of the mathematical model is the voltage at the DAC output depending on the code on the bit capacitors. The figure shows the lower section of the array with currents flowing at the moment of switching. In equations 1 and 2, there is a description of this structure according to the Kirchhoff's current rule. Laplace transform is used to replace differential equation number 2 to algebraic equation number 3. From expression number 3, dependence of phi 0 on the voltage on the bit capacitor and the voltage phi 1 can be deduced. Equation 4 shows a similar relationship after the inverse Laplace transform. When drawing up such equations for all sections, it is possible to obtain the dependence of V out and intermediate points on the voltage on the bit capacitor, and therefore on the code on the array. Expression 5 describes a similar dependence for a matrix of two sections, one capacitor in each. Next, we will take a quick look at the capacitor mismatch model and the noise model. As mentioned earlier, during manufacture, the capacitor size and capacitance is different from the intended one, which can be imagined as a capacitor connected in parallel to the main capacitor, which may have negative capacitance. To simulate the capacitor mismatch, the value of the uniform distribution function from 0 to 0.01 of the weight of the least significant capacitor in the section was randomly added or subtracted to the capacity of each capacitor. An additive source at one of the comparator inputs with a normal distribution with a standard deviation of 32 microvolts and a mathematical expectation of 0 volts was used as a noise model when the supply voltage is 3 voltage. And we now proceed directly to the algorithm. The capacity of each capacitor can be represented as the sum of the capacitances of the lower capacitors with an accuracy of half the capacitance of the lower capacitor. The concept of the weight of a capacitor is introduced, a dimensionless quantity that reflects its capacity. The weight of two adjacent capacitors reflects their inter-bit ratio. Knowing the weight of each capacitor, you can find out how much the inter-bit ratio has changed and adjust the output code as required. The algorithm works as follows. First, it is necessary to divide all capacitors into X calibrated and Y constant weights groups. Second step is assigning the weights to the junior capacitors based on their nominal capacity. Next, in the cycle, you have to calculate the weights of the highest capacitor from Y plus 1 to N. And the last step is calculating the full scale weights to generate the output code. The table shows the result of the model's operation when digitizing two 1,000 samples. The difference between the schematic model with ideal elements and the mathematical model is about 10 to the minus 9 power volts. And the speed of the mathematical model is from 10 to 12 times larger than the schematic models. The array consists of 3 sections with 6 capacitors in each one. As you can see, applying the algorithm increases the signal-to-noise ratio by 7.3 decibels or 1.1 effective number of bits. And as you can see from the graph on the right, spurious has decreased significantly, which improved the spurious free dynamic range by 60.8 decibels. Thus, the algorithm has shown its effectiveness. The simulation results with noise without mismatch and with mismatch are equal. And so here are my conclusions. Problem of ADC modeling at early stage. Classical approaches, the advantages and disadvantages were considered. Was proposed a mathematical model of the ADC, and the algorithm was finally verified. Thanks for your attention.